Yeah, hello, good morning. My name is Amine Bermak. I'm from the College of Science and Engineering at Hamad bin Khalifa University in Qatar. And today I'm going to talk about the Internet of Things, challenges and opportunities. So before I start the outline of my talk, I would like to share with you the current landscape with respect to IoT. IoT is today growing at a pace that is much higher than Moore's Law. It is expected that basically by 2021, there will be about 300 billion devices that will be connected to the internet. And this number is growing at an exponential pace. This means that basically IoT will be a major technological player in the industrial world and also in the near future. IoT suppliers and services provided are expected to grow to 26 billion units by 2021 or 2022. And applications, of course, include smart cities, smart homes, smart cars, agriculture, healthcare, and many more. So these are actually the trend to look for in the near future in terms of research and development. What are the key elements driving basically IoT? We can talk about security and privacy, because if you're going to put a lot of data on the internet, you need to secure it and you need to make it private. There will be also a lot of hardware development, advanced microcontroller, system on chip, sensor technology, because IoT, you can think about it as a sensor that is connected to wirelessly to the internet, and therefore sensing and also readout electronics, microcontrollers will be the main driver. We also have edge analytics, which means you want to do a lot of analytics on the cloud and also on the base station when you transmit the data. With IoT, there is a buzzword which is related to machine-to-machine automation. So basically, in the future, sensor devices, IoT systems will be all talking to each other without human intervention. So we're talking about machine-to-machine automation. In order to enable all of this, we need to deploy electronics at very large scale, and wearables is going to be a key segment within the overall IoT technology and the IoT market. So wearable, by wearable, we mean wearable sensors that are ubiquitous, and you can actually wear them, and they are embedded in clothing and other basically devices. We talk also about sensor fusion, because the number of sensors is going to explode in the future, and therefore, in order to make better intelligence, you have to analyze the data from a large number of sensors. So people are talking about sensor fusion as a very interesting area to consider in the near future. So I would like to talk about what are the range of applications related to IoT, Internet of Things. And in my opinion, we can divide them into two main categories. We're talking about massive IoT and also critical IoT. In massive IoT, we're talking about applications related to, let's say, smart building, logistics, smart meters, agriculture, and so on. And for all of these applications, basically volume is very important. So you need to target very low cost, very low energy, because you cannot go and calibrate, let's say, the sensors of an IoT device. So it has to be basically self-powered and also self-calibrated. So we're talking about very low energy, very low cost, and also massive number. Because if you're talking about smart agriculture, smart logistics, smart building, you're talking about a very large volume. We also have critical IoT. In the critical IoT, we can find applications such as remote healthcare, transport systems, industrial control, biomedical and remote surgery. And for this kind of application, it has to be very reliable. So the cost is not the first criteria. It has to be very reliable, very low latency, so there is no delay between action and reaction. So for example, if you're talking about applications related to remote surgery, latency has to be very low. And also very high availability. You cannot afford to lose the spectrum and the communication. So low latency and also high availability. With all these applications, there will be a lot of research in the wireless area. So we're talking about a new, basically wireless protocol that will be emerging in the future. And for example, we're seeing today things like very low energy Bluetooth, talking about LoRa and other type of wireless connectivity. So it can be divided into different categories: low range, low power, low range, high power, short range, moderate speed, and also short range, high speed. So today I'm going to try to talk about the IoT applications in the context of autonomous microsystems. And what I mean by autonomous microsystem is basically devices that can sense, process, and wirelessly communicate. And you're talking about various applications, for example, security, video surveillance, alert systems, connected cars, mobile applications, mobile-centric applications, public transportations, smart automation, and all of this will enable smart cities. So to basically address this kind of applications, in my opinion, there are three pillars. In fact, there are, I would say, four, but I will not talk about the fourth pillar. So the first area is going to be sensors. It's because if you talk about IoT, it means it's devices that can sense and interact with the real world, and then you need to generate sensing data. To make these IoT devices deployable at very large scale, you have to make them very low cost, very low power, and self-calibrated. So in the sensor area, I think the challenges would be really how to make the sensors self-calibrated, how to make them very low power, and eventually even self-powered. In the area of processing, because once all signals in the real world are analog, you need to convert them into digital world. So in the area of processing, there will be readout circuits, there will be also intelligent, what I call intelligent data converter, because we cannot rely on conventional ADC, analog to digital converters. We have to come up with intelligent data converters, and by that I mean basically these are converters that will try to sense information rather than data. In the area of communication, which is also a very important part, basically we're talking about very low power communication, and also trying to communicate information rather than data, if possible, and at the same time looking at energy harvesting as well. So within this context, I will try, my agenda today is to give you a few examples that address these three areas of basically sensing, processing, and communication. And I will try to do it for three case studies. First, IoT device, which is, in my opinion, a passive RFID. We're going to talk about that in the first part. And then I'm going to talk about an IoT device that is very special. It's actually an electronic nose that we are implementing in my group. So we'll see how we can achieve very low power electronic nose. By electronic nose, we mean basically a device that can smell, and there are many applications for this kind of device. So we'll look at calibration, how you train the system in order to detect different odors and different gases and so on. And then I will talk last about the vision sensors. And the idea is actually to look at wireless camera network. So the idea is actually to have very low power vision sensor that you can deploy as an IoT node. And it's actually a sensor that can harvest the energy from the environment, and it can be self-powered. And it is also equipped with analog to information converter, AIC. So let me start with probably, in my opinion, what is really the first IoT device. IoT is a buzzword today, but in my opinion, it started more than 2 decades ago when people were talking about RFID, radio frequency identification chip. And in this example, I'm going to show you one of the RFID that we designed in my group. And it's actually a passive sensor tag, which means it's a passive RFID, which means you don't have any battery. It's self-powered. And also, it includes sensing capabilities. So not only identification, but also sensing capability. And we included a temperature sensor with this RFID. To me, this is one of the very first IoT, because you can actually wirelessly communicate the information, and you can sense information from the real world. And in addition to that, you can add an ID to the product or the chip that you have. So the challenge with this kind of application is because it's a passive RFID, it means that basically you have to harvest the energy somehow. And the idea here is to use the reader itself in order to harvest the energy, because the reader typically will send a wave, an RF wave, in order to interrogate the ID of the chip. And the idea would be actually to use that RF signal in order to self-power the chip and to do some sensing capabilities, to do sensing functionalities, and to send back to the reader basically information related to the temperature and also the ID. So you can imagine a lot of applications for this kind of device, which will be in logistics, especially with products that are temperature sensitive. So to do that, it's actually not easy in terms of IC design, because you are talking about a very complicated system on chip, where you need to have a memory inside to store data and the ID of the product. You need the communications. We have a digital baseband. You need sensing capabilities. You need to generate the clock. You need to modulate and demodulation for the communication. And this is a transceiver. You receive a signal and you send back a signal. So all of that, because it's passive, it needs to work at very, very low power. So you need to have a power management unit and an energy harvesting unit. And in order to do that, actually, we did that with a very simple idea where, because the sensor has to consume very little power, the power budget of the whole chip is very low. And therefore, we had to come up with innovative way of sensing temperature. And you can imagine that if you use just an inverter in electronics, we know that the delay of a simple inverter typically is proportional to temperature, because you have parameters such as mobility of the electron in a transistor and also the threshold voltage of the transistor that are temperature dependent. So we studied the dependence of basically a simple delay, and we come up with this architecture that uses this feature. So the key idea of this architecture is that basically it has, I would say, 4 components. The first component is a delay generation circuit that is proportional to temperature, PTAT delay generator. So when basically the temperature increases, this output will give you a pulse with a delay that will increase with temperature. So it's proportional. And then we use the same approach, but in a reverse way, in a complementary way, to realize a CTAT delay generator. And at the same time, we have basically a supply voltage sensor. So basically, when your supply is changing, you can actually sense that, and you can inject it as a parameter in these 2 blocks. What is the key idea of this? So this is very important because basically we are trying to harvest the energy from the RF signal. So RF signal, we know that it's a DC signal, an AC signal, sorry. If it is an AC signal, it means that it's fluctuating a lot. And even if you use a power management unit, you will have a lot of ripple in your signal. And we know that the delay also depends on the supply voltage. So if you have your supply that is very dirty, it's not very clean, and it's not a clean DC signal, you end up with variation in the delay. And therefore, you cannot tell whether this is temperature or it's the ripple in the supply. So we had to basically add a supply voltage sensor and inject it as a parameter to compensate for that. Another very important, interesting idea of this is that the output will give you 2 pulses, one that increases temperature, the other decreases temperature, and therefore at the output you have like rising and falling edge of the pulse. And therefore you don't need an ADC because it's just a pulse that you need to digitize. So this is ADC free, it's analog to digital converter free architecture, and therefore you can reduce the power a lot. So this is actually some of the simulation and experimental results. We can see that with temperature, our pulses is going to increase in a differential way. This is actually the chip that we realized. To me, this is a real IoT device, which includes temperature sensing. And we can see that actually at that time we achieve a very, very low power, basically type of. So we realize a very low power type, very low power consumption at that time, which is very interesting. So let me continue. The second case study is related to an electronic nose application, where the idea is actually to design a device that can basically smell. It's an electronic nose. And you can imagine that we have multiple applications related to automobile, food quality monitoring, medical applications, air quality, safety, and so on. In fact, there is a very large number of applications in this area related to, for example, gas leakage, production processes, and quality control in the food industry, and even biomedical applications, because recently there are a lot of evidence that show that some bacteria and viruses actually they are associated and recognized with the smell. And therefore, if you have basically a very sensitive electronic nose, you can even detect bacteria and viruses. So in this project, we actually try to build a whole system, going not only from the sensor, but all the way to the communication. So it's really an IoT device. So the idea is to have a gas sensing array, and then we acquire the data, and then even we do the encoding and classification and the wireless communication. So the idea is actually to recognize the smell to be able to train the system to recognize new smells. So there is an AI and machine learning algorithm behind. And also all of this needs to be integrated at a very compact area, and also consuming very low power, and it's low cost and robust because we want to deploy it as an IoT device. So to do that, actually, we in my group, we looked at the tin oxide gas sensors. And these are actually MEMS structure. And the idea is that you have a sensing film, and this sensing film, you have a heater underneath. So when you heat the sensing film at high temperature, this can be a sensing material, there will be an oxidation reaction. And the idea is, once you have an oxidation reaction, because the sensing film will interact with this odorant and these molecules, and therefore, by oxidation, you're going to gain or lose an electron in the structure. And therefore, your resistance is going to vary. But the problem, the resistance is going to vary depending on many parameters, for example, humidity as well, because you have molecule of water that will deposit on the sensing film. So in order to overcome the selectivity problem, we try to build an array of these. And each sensor within the array is tuned differently by using either different catalyst or doping. So we use different material and also use doping of these materials. So we end up with basically, let's say, 4x4 sensors, and each sensor is unique because you're using either a different catalyst or a different doping in order to obtain some kind of fingerprint signature for the sensor. So this is actually the MEMS structure. You can see that it's a suspended film. Underneath you have heaters, which can be just polysilicon where you apply a certain current. And then you need to isolate the device from the rest of the substrate. So we use a bridge in order to do that. So this is actually sensor electrodes, and you have a bridge. And underneath, you see this structure here is actually a micro heater, which can be just polysilicon. Now, if you try to look at, once you have the array, you're going to basically expose the array to a certain smell, certain gas, and you try to detect the output. So if you try to use just the sensor response as a feature, which is typically the resistance of the sensor, and you try to model that, we end up with a quite complicated function, which depends not only on the gases that you are exposed to, but also concentration and also the parameter of the material you are using for that sensing film. And typically, it's a power-low relationship, and this is very well documented. All tin oxide sensors usually obey to this kind of law, where parameters depend on the gases, but also on the sensing material that you use, and it's very hard to actually model this function. So if you want to extract these parameters, alpha and gamma, it will require accurate measurements of gas concentration, because you need to expose the sensor and also control the concentration in order to reduce your model. So the key question that we ask, what kind of features should we use? Is it just the resistance of the sensor? And features are very important. As you know, if you use the right feature, then the classification can become much easier later if you implement the machine learning. So looking at the sensor response, we know that it's power low. So in my group, we thought maybe if we use a log response, then the concentration becomes additive, and we can have this kind of relationship. Now, if we try to do it in a differential way, exactly in the same way I explained about the temperature sensor, where we have complementary and proportional path, and we try to read it in a differential way. So we thought maybe instead of reading just the log response of one sensor, maybe we should also have another sensor that we use as a reference. So sensor 1 here in blue represents a certain reference. And then the idea would be to read in a differential way. So instead of reading sensor I will try to read the log of sensor I minus the log of sensor 1, which represents a reference. If you do that, then basically you get rid of the concentration. And because it's additive, you read in differential way, you eliminate the gas concentration. So basically, this means that if you want to model the response, you don't need to know the concentration in an accurate way. So based on this idea, we ask ourselves the question, how do we use that feature? And we come up with a very interesting idea where instead of representing the log of the resistance of each sensor, what we can do is actually we can generate a spike. So you have an array of sensors, and for each sensor within the array, you generate a spike that is proportional to the log. And basically, if you have 4x4 sensors, each one of them will give you a spike, let's say. And the timing of that spike will be basically a feature. So if you have gases that are exposed to your sensor array, you generate spikes, and for each gas you will have a certain spike pattern, and this spike pattern can be actually associated with a given gas. What is really interesting about this is that if you have, let's say, a gas that is exposed to your sensor array, then what's going to happen is you have a spiking pattern, and each sensor within the array is going to spike at a different time. So for example, here I represent sensor 3 as the sensor located at column 3, first row, third column, and so on. So I can encode the gas with the spike pattern associated to it. What is really interesting about this is that we have seen in the previous modeling that if the time of the spike is proportional to the log, then the difference of two spikes is concentration independent. This means that if I change the concentration, the order will not change, because basically that difference that you have here is independent on concentration. So this means that this spike pattern is going to be the same for every concentration of the same gas. The only thing that you're going to have is going to be just a shift in the whole pattern. So here, if you have an unknown gas that comes in, you will have a certain spike pattern. If you change the concentration, that pattern will not change, and you have just a shift. This is modeled in the previous equation that I showed you, where actually basically the difference of the two logs is actually independent on concentration. This is what it means. So using that feature, actually, we can build a classifier, a very easy classifier that is just a lookup table, because you can store all of these gases that you put into the system and you recognize. You can store them in the lookup table. When you have an unknown gas, you generate a certain pattern, and you just actually basically perform some kind of nearest neighbor to recognize what kind of pattern is that as compared to the ones that you stored in the memory. So the recognition becomes very easy, the training even simpler, because training here, you just present an unknown gas and you label it and you store it in the memory. That's it. So very interesting idea. So inter-spike pattern, if you vary the concentration, as I told you, and mathematically you can prove it, you're going to have exactly the same spike pattern, but when you change the concentration, it's just a shift. So with this system, actually, you don't only recognize gases, but in fact, you can also quantify, because the shift will give you the concentration. So the time to first spike is going to give you the relative concentration that you have for that particular gas. Now, how can we build this into an IoT device on an integrated system? It's actually very interesting, the implementation that we did, and we did it in a very simple way. So we need to compute, let's summarize. We need to compute the log. We need to generate a spike that is proportional to the log. And then we need to do that for the whole array. And then the recognition would be just basically comparing this spike pattern with what we have in the memory. So basically, classification becomes just a rank order and looking at the spike pattern. So how can we build this? So the first thing you need to do is to convert the resistance into a log of a resistance, and then to generate the spike. So this part here can be very easily done. So imagine that your sensors are actually resistive. So you have an array of resistances, and you want to compute the log. One way to do it is actually to have a current source. You just charge this output to a certain level, and then after that you discharge it through a capacitor, and you compare the voltage of this discharge with a comparator at a certain reference voltage, and whenever you reach the reference voltage, you generate a spike. This can all be realized in a simple RC circuit. And if you look at basically the voltage of this output, because it's an RC circuit, we know that the voltage is equal to exponential of the time over RC, okay? Which means that the time to reach the threshold is a log function of the voltage. So remember, the voltage in an RC circuit is equal to exponential of T over RC. If I do the log of the voltage, it's T over RC. So the time to reach the threshold, or the time constant, the time to reach the threshold is actually proportional to the log of the voltage. Now, what is the voltage? Voltage is Ri, because I just use a current source to charge through my sensor. So it's Ri. So the log of the voltage is actually the log of the resistance, and this is exactly what we want. So basically, when you reach that threshold, at that time, you are actually computing the log of the resistance, and you generate a spike. So all is done in a very simple RC circuit. And you can see that basically we can generate that spike and use it for the classification. So this is explaining this idea, and what is nice about this is that you don't need an ADC as well, because you generate just a spike, and the spike is going to be used in order to recognize the gases. It's ADC free, so it can be very low power. So we built a system, an IoT system based on this idea, and actually it's equipped with Bluetooth, which means that the classification output can be, and even the response of the sensor can be communicated to, let's say, your mobile device or a portable device. All right, so recently we are also working on increasing this sensing array, because the more sensors you have, the more signature you will have, the more functionality or detection you can add to your electronic nose. Because we are not trying to build basically a device that detects certain gases. We are trying to build an electronic nose, which means that it can detect multiple gases and classify them. So recently we built some kind of imager that is you acquire the gases in this sensing array, and it gives you an image that is basically looks like an image, but in fact it's gas sensing. So the idea is to actually use floating gates as sensing device, and we have an array of these floating gates, 16 by 8, and the floating gate, as you know, the idea is you have a floating gate, and there what we do is we deposit some polymers on the floating gate, and therefore when you have gases that deposit on the floating gate, it's gonna basically it's gonna affect the basically the operating function of the transistor, and therefore the threshold voltage of the transistor will be shifted. So by measuring the threshold voltage of the transistor, in fact, you are actually measuring what kind of basically material or molecules are depositing on the floating gate. And the idea is actually to do it as an imager, so it includes not only the sensor array, but a SAR ADC and all the control that is integrated in a single chip. This is, in my opinion, the very first single chip gas sensor that exists out there. So you can see by doing this, when you expose the sensor array to gases, you will have a pattern, an image. And this is, for example, acetone response pattern. This is formaldehyde response pattern. And we can use actually all type of like LDA, PCA, and other machine learning algorithms in order to basically classify the different gases. So what is really interesting about this is that we can implement a very large array of these. We can have basically a sensor area that is very small. We can also consume very little power because all of this can work at room temperature. So let me see the time that is left. I think I have very little time left for my talk. So I'm gonna just try to conclude. In fact, I was trying to also show you some of the application that we have for image sensing, but I don't think I have time for this. So I will try to basically move right now to the conclusion. So IoT devices involve sensing, processing, and communication. In my opinion, we have a lot of challenges, and some of these challenges are related to low power, energy harvesting, and also information-based converter, because the idea is actually to try to sample basically information rather than the whole data in your sensor. In fact, if you look at the two sensors that I showed you, or the 2 case study, which is the temperature sensing and also the electronic nose, you will notice that the theme in my presentation is actually time domain. So basically, all the information is converted into a time domain. If you look at the temperature sensor, we generate a pulse. If you look at the electronic nose, for each gas, we actually generate a pattern. So it's time domain. And time domain actually encoding is very interesting because it gives you immunity against dynamic range reduction. It also gives you immunity against noise because you are generating a pulse rather than dealing with an analog signal. And also you can have reduced power because your data is represented in a spike. It's very promising for processing as well because time domain gives you a lot of ways to process the data in time domain, which involves just the implementation of counters and timers and so on. So IoT devices are today a reality for some devices, but still challenging for other areas. And I believe in this area of research, there are still hurdles and difficulties in all areas related to sensors, IC design, signal processing, and communication. But eventually, these difficulties will lead to more opportunities for innovation, and that's what we are doing as academics. And I would like to conclude with that. Thank you very much.